Hello everyone and welcome back to CS 184 discussion recordings. Today we're going to be going over splines and curves, so let's get started. So the first thing we're going to talk about is polynomial interpolation. So basically what this is we have some points and potentially some derivatives, and what we want to do is we want to find a curve that goes through these points and has these derivatives. And so we'll see a few ways to do this, and there's a more in-depth introduction in lecture, but we're just going to kind of go over some examples here. So let's get started. So the first question says, list all degree 2 polynomials satisfying f of 0 is 1, f of 1 is 2, and f of 2 is 5. So the first thing to keep in mind here is that in order to uniquely specify a degree 2 polynomial, we need 3 points, and that's what we have here. So when it says list all degree 2 polynomials, we know that there can only be one. So there's one unique solution. So let's go ahead and find this. So let's call our polynomial f of t, and we can write it something like this. Plus bt plus c, right? This is the general form for a degree 2 polynomial. And so right off the bat, we know f of 0 is equal to 1. And so if we plugged in 0, that's very simply gives us c is equal to 1, right? Now the next one, we plug in f of 1 is equal to 2. So plug in 1 for t, and we get a plus b plus c is equal to 2. Okay, and then let's plug in 2 for t. So then we get t squared. So 4a plus 2b plus c is equal to 5. Whoops, 5. Okay, so now we have 3 unknowns and 3 equations. We can go ahead and solve. I'm not going to solve the system of equations right here, but what we end up doing what we end up getting is a is equal to 1, b is equal to 0, and c is equal to 1. So we can essentially write f of t is equal to t squared plus 1. Okay, and if you plug that in, I think you'll see that you get the right answer. So there we go. That's our degree 2 polynomial. Now the question asks, what about degree 3? Okay, so one way to do this is we could say, okay, if we want some degree 3 polynomial, here, let me just draw a line. We could write this as a composition, as one polynomial as the sum of 2 polynomials, right? And then what we could do is we could say, well, let's make f1 equal to t squared plus 1, which is a polynomial we already know satisfies these 3 points. And then we can impose some constraints such that f2 at 0 is equal to f2 at 1 is equal to f2 at 2 is equal to 0. So essentially this new composition f of t will still satisfy all 3 of these points, right? So let's go ahead and see how we can do this. And so f2 is going to have the following form. It's going to look a little something like this: a t cubed plus bt squared plus ct plus d, right? And so if we do kind of exactly what we did last time, we plug it in. So we're going to get d is equal to 0. We're going to get a plus b plus c plus d is equal to 0. And we're going to get 8a, whoops, that zoomed in way too much. Okay, 8a plus 4b plus 2c plus d is equal to 0. Okay, and so now essentially we have 4 unknowns and 3 equations, so we can still go ahead and solve, but we're not going to come out to exactly one answer. And the reason for that is that there's multiple polynomials that could satisfy this. Remember earlier on I said if we want to have a degree 2 polynomial, we need 3 points. Here we're looking for a degree 3 polynomial, but we only have 3 points. So we can't find a unique polynomial. There's a bunch of solutions. And so if we go ahead and solve this, what we're going to get is b is equal to negative 3a and c is equal to 2a. And we already know d is equal to 0, and we can use any a in this situation. Okay, so that's where the multitude of solutions come into the picture. And so putting this all together, essentially, now we can go back to this original composition formula we wrote, and we can get f of t is equal to t squared plus 1 plus a times t cubed, right? That's just directly out of the formula. And then now b is going to become negative 3, so minus 3t squared. And then c is 2, so plus 2t. And then d is 0, so that's it. And there we go. There is our solution. Okay? So the key here is plugging it in, getting a system of equations, solving, but always keep in mind, for a degree d polynomial, we need d plus 1 points to find a unique solution. Okay, let's keep going. So the next question says, suppose we have a list of constraints. So we have f of 0, f prime at 0, f at 1, f prime at 1, all the way up to fk. So we have a lot of possible constraints. And so if we want to find this function f, there's multiple ways to do it. One of them is to solve for a single dk plus 1 degree polynomial. So just one polynomial goes through all these points, has all these derivatives, just one thing. Or we can fit k separate cubic Hermite splites. So that would be k cubic polynomials that would also go through these points, also have these derivatives, but they would be multiple polynomials that we all put together. Okay, so what this question is asking, or what are the trade-offs here? So let's go ahead and check the actual discussion solutions for this. It goes into a lot more detail than I will here, but I'm just going to go over kind of the key points, and so we can see. So one option is the single polynomial that's over there, and then the opposite is the Hermite splines, right? Okay, so the single polynomial, one of the big thing is infinitely many continuous derivatives. Okay, because it is one polynomial, it's continuous everywhere in our range. So continuous derivatives. Okay, that's a big thing. That generally is useful. We don't have to ever worry that we're gonna differentiate and get something weird, get some weird numbers. Okay, one issue is though, if we change a control point, change 1 point, it could change the whole polynomial, right? Because the polynomial has to go through all of them, and it's just one polynomial going through everything. So just changing 1 point could really change up what our polynomial looks like. So now let's talk about the Hermite splines. So the Hermite spline, rather than one polynomial, it's a bunch of cubic polynomials all put together. And so what that tells us is it will be continuous, and it will have continuous derivative, but it may have discontinuous second derivatives at the control points. We know we'll have a smooth derivative, but maybe not a smooth second derivative, okay? And so that's kind of important, keep that in mind. But there is a positive here, and that is that changing 1 point, wow, that was terrible. Change 1 point will only change the 2 splines on either side of it. So 2 splines. Okay? So once again, look through the discussion solutions for some more details, and then also on the project you guys will get to play with this yourself, and that should give you some more intuition on the pros and cons of both sides. Okay? So let's keep going. So number 3, a cubic polynomial f of t is equal to at cubed plus bt squared plus ct plus d is uniquely determined by specifying both its values and second derivatives at t equals 0 and t equals 1. So this is, and here's the key, we're talking second derivatives, not first derivatives, which we use in Hermite interpolation. So given these 4 things, f of 0, 1, double prime, f double prime 0, and f double prime 1, let's write a system of equations, okay? So they gave us f of t, so let's write f prime of t first. And so what is that going to be? It's going to be 3t squared plus 2bt, whoops, that should have an a, plus c, right? That's that. And then now let's write the second derivative. So f prime of t is going to be 6at plus 2b, okay? So just simple derivatives. And then now we can just write it. So f of 0, just like we did above, we plug in 0, everything except for d goes away. So f of 0 is equal to d. Simple. F of 1, we plug in 1, all the t's disappear, it just becomes a plus b plus c plus d. Okay? Now let's look at the second derivative. So f double prime at 0. Well, we plug in 0, the first term disappears and we get 2b, right? And then f double prime at 1, we plug in 1, and so the first term becomes 6a, and the 2b stays the same. So there we go. These are our 4 equations. We have 4 unknowns, and we can solve. Okay, so let's keep going. We're not going to solve in this question. We're going to keep going, and we'll find it later. So now it says, write the matrix which you would invert, and apply to the vector f of 0, f of 1, f double prime at 0, f double prime at 1, to recover a, b, c, and d in the previous problem. Okay, so what we've done here in problem 3 is write a system of equations. We have 4 equations and 4 unknowns. So let's reformulate this into a matrix vector multiplication. Okay, so what we're going to have is we're going to have some matrix times a, b, c, and d, and that's going to be equal to f of 0, f of 1, f double prime at 0, and f double prime at 1. Sorry, that's super messy. Okay, so now let's see. We just have to read off these equations we wrote just above and just write down. So f of 0, it's just d, so 0, 0, 0, 1, right? And then f of 1 is a, b, c, and d, so 1, 1, 1, 1. F prime at 0 is just 2b, so 0, 2, 0, 0. And then f prime at 1 is 6a plus 2b and nothing c and d. Okay, so there we go. And so now, this goes back to our math introduction. We want to find a, b, c, and d. These are the real unknowns of the problem. So how do we do this? Well, this matrix that we've written, we take the inverse of it, multiply by both sides, and there we go, we can solve, right? So this matrix right here, that is the matrix that we would invert and then apply to this vector on the right to recover a, b, c, and d. Okay, so that's our answer right there. Okay, so let's keep going and actually solve this. So now 5 says, invert this matrix and use its columns to identify 4 basis polynomials for this problem. Okay, so matrix inversion is a little bit complicated, especially for 4x4 matrices, and it's not super in depth or covered in 184. So I'm just going to go ahead and give you guys the answer, and then you guys can look up how to solve it on your own or just use a calculator, and that's totally fine. So let's go ahead and write this out. So A, B, C, and D is equal to, okay, so here is where I'm just going to give you the inverse. So 0, 0, 0, 0. And once again, you can verify this online. There's plenty of inverse calculators, or you could do it by hand, but that can get kind of tedious for a 4x4. Okay. So there, and then let me write out this. F double prime at 0, F double prime at 1. Okay, so this, what we have here is essentially just a reformulation of this. We took the inverse, multiplied by both sides, and we get this new equation. So now we move on to the next part of the problem, which says use its columns to identify 4 basis polynomials for this problem. So if you want more depth on this, look through the lecture. It goes through the idea of exactly why these are the basis polynomials. But essentially what the idea is that we're using some linear combination of these columns to get our final polynomial. And so we're just going to read this right off the column. And this is a degree 3 polynomial, which is why we have 4 rows. So let's just go ahead and read off. So G0, which is the first basis polynomial, first column, it's 0, 0, so no cube, no square. It's just going to be negative t plus 1. Okay, read off the first column. The second one, G1, 0, 0, just t, right? Pretty straightforward. Now we look at this third column, so G2 is equal to, now we have, some actual numbers. So it's going to be t cubed over 6, that's the first one, plus t squared over 2 minus t over 3, right? And then the last one is 0, so there's no constant in this case. And then let's go ahead and look at the last column. So that's going to be t cubed once again over 6, not negative, and then 0, and then minus t over 6. Okay, so there we go. These are our 4 basis functions. Sorry, I ran out of space a little bit, but there we go. So we inverted the matrix and then just read off the columns. And once again, go check out the lecture for a little more in-depth explanation of this. Okay, so let's keep on going. So now we're going to talk about I don't even really know how to say it, algorithm. And so what this algorithm allows us to do is create a smooth Bezier curve from a series of control points. So essentially, we give it points, and then it creates us a nice smooth curve between these. And the way it does this, the central technique to this entire algorithm is LERP, or linear interpolation. And so here's a little brief introduction to LERP. It's very simple. Essentially, you have 2 points and some value, and the LERP just does a linear combination of these points. And so the parameter in this case is this t right here. Let me switch to red. So that t right there, and this t has to be between 0 and 1, and then the LERP just does 1 minus t times 1 point plus t times the other point. Okay, so it's a very simple basic building block, but as you'll see in a second, you can put this together and combine it to make some really powerful algorithms and some really nice curves. So let's go ahead and do some practice. So for a Bezier curve defined by 3 control points, what is the degree of the polynomial you get from the algorithm? Okay, what about for endpoints? So this is going to once again go back to something we talked about earlier, which is, for a degree d polynomial, you need d plus 1 points to uniquely determine it. And so since this algorithm is uniquely determining it for 3 control points, we know that we're going to get a quadratic, or degree 2. Okay, and similarly for endpoints, we're going to get a degree n minus 1 polynomial. So actually, I guess this one's kind of confusing, but anyway, so 3 control points, 3 points, we get a quadratic, n points, we get an n minus 1 degree polynomial. Okay, and so you'll actually see the math of how this works out in just a little bit when we walk through it. So let's keep going. So before we get into the math, let's do some visual examples of how this algorithm is used. So just to give you some intuition on what's actually happening. And I'm going to apologize in advance. My lines are not going to be super straight, but I think they'll get the point across just fine. So we want to use this algorithm to find the point where t is equal to 1/2 on the Bezier curve. So now remember, what it does is a set of linear interpolations. Basically, in this case, with t equals 1/2, we're averaging. So what does that mean for visually? On the first linear interpolation between p0 and p1, it's going to be this point, right in the center. Between p1 and p2, similar thing, right in the center. p2 and p3, once again, right there in the center. Then what we do is we connect these points with lines. Okay? And so now we've gone from the first level of control points, p0 through p4, to the next level of control points. And notice now we have 3, where we had 4 before, now we have 3. And so then we just do it again. So now we're going to find this midpoint and this midpoint, connect them again. Now we have 2 control points. Do the linear interpolation again. That's 1/2. Here, let me put it in red. And there we go. That's our point. That's the point where t is equal to 1/2 on this Bezier curve. And so now you may be thinking, well, this is just one point. How does this help us? Well, what this algorithm will do is essentially it'll test every t from 0 to 1. Each of those will give you a different point. And when you put all those points together, that's the curve. That's the Bezier curve. Okay, so this is just one point on the curve that this algorithm will give us. So let's keep going. Let's do another example. This time t is equal to 1/3. Okay, so let's see what this one looks like. So once again, we start with linear interpolation. So p0, p1, let's go this time. Instead of going halfway, we're just going to go 1/3 of the way. So maybe about there, and then about there, and then about there. Okay, so now we connect these up. We've gone from 4 control points to 3. Do the same thing again. So about there, connect it up. Now we're down to 2 control points, and once again, do it in red. We go 1/3 of the way over, and there we go. That's our point. Okay, so this is for t equals 1/3. If we had done t equals 1/2, we would have had a different point, and so on and so forth for every single one. So this is, we can say f at 1/3, and up here we can say this is f at 1/2. Okay, and so when we put all the f of 0 to f of 1, all those points together, we get the curve. Okay, so now that we have somewhat of a geometric understanding, let's go through the actual math and see how this works out. So we're gonna go back to the answer of that first question, where, given the number of control points, what degree polynomial are we gonna get? So let's go ahead and start. So we have control points p0 through p3, right? That's our level 1. Now we apply the first level of linear interpolation. It's the first round. And so what we're going to get is L1. It's going to be, so here s is equal to 1 minus t, and then t is equal to, well, t. So s times p0 plus t times p1, right? That's one linear interpolation. S times p, what's happening? P1 plus t times p2, and then s times p2 plus t times p3. Okay, so that's our first level of interpolation. Notice how we went from 4 points to 3. And so that's this level. We went from p0, p1, p2, p3 to these points right there. To, here, let me just, there, and there. That's what we just solved for. Okay, so now we have level 1. Let's go ahead and solve for level 2. Okay, and so now what we're going to do, just like we combined the 4 control points, we're going to combine these 3 control points. Okay, so it's going to be s times this plus t times that. And so if we go ahead and write it out, it's going to look, and I'm going to skip a simplification step, but it's just, multiplication, simplification. So it's going to be s squared p0 plus stp1 plus stp1 plus t squared p2. Okay, and so it's s squared p0 plus 2stp1 plus t squared p2. And so then this was for the first 2 points, but we can do the same thing for the second and third point. And so we'll just get something that looks very similar, just shifted. So it's going to be s squared p1 plus 2stp2 plus t squared p3. Okay, so now what we've done is we had 4 here, 4 control points, then we had 3 here, and now we're down to 2 here, right? So now we're at this stage. We have this point and this point. So we're almost there. We just have to do one more linear interpolation and we'll have our final point. So let's go ahead and do that. So this is going to be level 3. And so now it's going to be this times s plus this times t. Okay? So let's go ahead and do it. So it's going to be s cubed p naught plus 2s squared t p1 plus st squared p2 plus s squared t p1 plus 2st squared p2, whoops, ran out of space a little bit, but plus t cubed p3. And so you might notice we have a few overlaps. So p1, s squared t p1 shows up twice, st squared p2 shows up twice. So we can simplify this a little bit. S cubed p naught plus 3 s squared t p1 plus 3 st squared p2 plus t cubed p3. And there we go. That is the final equation for the polynomial that we get, the Bezier curve that we get. And so you can see this is a function of s, and it's a function of t. So that's what we're using. And another thing you can see is we started with 4 control points up here, and we have a degree 3 polynomial down here, right? Degree 3 polynomial. So this is, going back all the way up here, divided by this. If it was defined by 3 control points, we got degree 2, n points n minus 1, and we see that the math does actually work out. We started with 4 points, and we end up with the degree 3 polynomial. Okay? So there's the actual math behind the Bezier curve, following the geometric intuition. And so, okay, the last part of this discussion, very last bit, is this matrix product. Okay, so it's matrix product, has some s's and t's in there, and the hint says don't expand it. Instead, think about what each matrix in the product does and how are they related to the algorithm. Okay, so in order to do this, let's do something small. Let's add a vector right here. So it's going to be p0, p1, p2, and p3. Wow, that was terrible. What the heck? Okay, sorry about that. Let me try again. P0, P1, P2, and P3. So this vector is massive, but now if you think about this, right, let's look at this very first matrix vector multiplication, right? It's going to be s times P0 plus t times P1, and s times P1 plus t times P2, and s times P2 plus t times P3. But let's come back up here. That's exactly what we did here, right? If you look at this, s times P0 plus t times P1, that's the first element in this matrix vector multiplication, and the second is sp1 plus tp2. So essentially, this first level of matrix vector multiplication, this one right here, is going to solve for our level 1 points. It's going to give us 3 points. And then if we look at the next round, then it's going to be s times the first point plus t times the second, and s times the second plus t times the third. But that's exactly what we did here in level 2. Right there. S times the first plus t times the second, and s times the second plus t times the third. And then if we come down here for the last time, it's going to be s times the first and t times the second, which is exactly what we did right here in level 3, right? S times the first plus t times the second, and we got 1 point. So essentially all this matrix product is it's doing the algorithm and giving us this polynomial in the end. So if we were to actually multiply this out, what we would get would be exactly what we got in the problem right above. We would get s cubed p0 plus 3s squared t p1 plus 3st squared p2, whoops, plus t cubed p3. And you can verify this. You can go through, do the matrix multiplications, and you'll see that you get the exact same thing. But it's more important that you look through this and understand exactly how these matrix multiplications represent exactly the same operations we did right here in number 4. All it is s times one point plus t times another, s times one point plus t times another. And each time we have one less control point, which is why these matrices go from, a 3 by 4 to a 2 by 3 to a 1 by 2. And eventually we have a nice equation for our Bezier curve. Okay, so that's all there is for this discussion. Just a little introduction to Bezier curves and splines, and I'll see you next week for more.